All right, let's get rolling. Welcome to day 2 of the Apalachicola ANERR Research Symposium. Thank you so much for joining us this morning. We have several talks this morning about listed species, bay productivity, and then we'll wrap up with some information about current sea level rise projections and the impacts, potential impacts to Apalachicola Bay. It's going to be an interesting morning. Just a few housekeeping items. Everybody is currently in listen-only mode. Well, let me run down the slide. Kennedy's going to keep me straight. First of all, the webinar is being recorded, and following the symposium in a few days, we will post the recording on the reserve's website, apalachicolareserve.com. And you can visit there and listen to any of the talks that you may have missed yesterday. The agenda for today's webinar is located under the Handouts tab. And at the top of the agenda is the link to the Padlet. And so the Padlet is a neat way to connect with any of our speakers. You can add in a comment. You do need to add your name within that comment so that they can then reach out to you, probably name and email. And I do see some comments from yesterday, so we will reach out to the speakers and make sure that they are checking in to see what comments they need to or questions they need to answer. During the webinar, after each of the talks, we'll have 5 minutes for questions and answers. To ask a question, you may either enter the question under the questions box, or you may raise your hand, raise hand, little hand over on the right side. Click on that, and we will take you off mute, and you guys unmute yourself, and we'll let you ask your question. So the last thing I'll mention is after the symposium wraps up, we will send out an email to all of the participants to evaluate the symposium. We'd really appreciate feedback on how it went and make improvements. So next year, when we do this, we can continue to have a great symposium. And I think it's been really great so far. I've certainly enjoyed listening to all the different talks and watching people make connections. It's just amazing. So with that, I will tee up our first speaker. It's Dr. Matt Ware from the Florida State University. The title of Matt's talk is Exposure and Consequences of Wave Washover for Loggerhead Sea Turtles in the Florida Panhandle. So Matt, welcome, and I'll let you take it away.
Awesome. Can you guys hear me okay?
Yes.
All right, now let's see if I can advance the slides. Sweet. All right. Good morning, everyone. Thank you for attending my talk this morning, and I hope you guys have been enjoying the symposium so far. I'm looking forward to the rest of the talks today. So to get us started this morning, I'm going to run down some of the work that I and my collaborators have done over the last 2 years, looking at exposure and consequences of wave washover for loggerhead sea turtle nests in the northern Gulf of Mexico. Before I get started, I'd like to acknowledge the folks that funded this work, mostly the folks running the Sea Turtle Grants program. So thank you all if you have the Sea Turtle license plate. It's greatly appreciated, your guys' contribution to sea turtle conservation. I'd also like to thank all the volunteers that put in a lot of hours on beach patrol, both on St. George Island and throughout the northern Gulf of Mexico, who they put in a lot of effort to protecting these species. They care a lot about them. Thank you so much for your work, and please keep it going. And then thank you guys for putting this whole symposium together. It's really appreciated. So what's the big deal with waves? Why do we care if the sea turtle nests get a little wet? Sea turtles, in order for them to properly incubate, they have a pretty narrow range of environmental conditions regarding temperature, salinity, and gas exchange with the surrounding environment that they have to be able to maintain in order to develop properly over the roughly 2 months of their incubation. when you introduce waves into this scenario, as you see, on a natural beach, on the most extreme end, when you have those waves that will wash the nests away, they're going to be in the surf, they're underwater, they're going to drown. So we lose quite a few nests on the most extreme end to those nests just getting washed away. Even if the nest manages to stay on the beach after it gets wet, excuse me, that increased moisture, that reduced gas exchange, that increased salinity, if it's prolonged enough, can result in embryonic mortality. And if not, it can alter the environmental conditions that will drive hatchling locomotor function, size, and sex ratios. Unfortunately, this threat for wave exposure is increasing, both from increasing hurricane frequency, intensity, and changes in timing that overlaps more with the nesting season. And then on the anthropogenic side, coastal squeeze, that we love to go to the beach. We love tourism on the beach. We love to live at the beach. So we're building a lot of infrastructure behind the beach to support that. But that means that as sea levels rise, as beaches try to move, they don't have anywhere to migrate inland. So you're getting this narrowing of the beach. So the turtles have less area to nest in. They're potentially more exposed to the waves as they're losing some of that nesting habitat. But it's not all doom and gloom. There are some natural defenses that sea turtles have to wave exposure since they've been dealing with this threat for millions of years. On one hand, you've got the mass production of eggs. Sea turtle females will lay multiple clutches within a season. They vary that nest site selection using different environmental cues like beach elevation, beach slope, or distance to the high tide line. And it's not exactly a small scale effort. So on average, you've got about 100 eggs per clutch if you're laying multiple clutches per season, and you do that over the course of a 20 or 30 year reproductive lifespan. A single female may lay up to tens of thousands of eggs in her lifetime. So some losses are to be expected. The wave exposure itself is also not inherently lethal. Just because a nest gets wet does not mean that all is lost. There is a tolerance to that exposure up to a certain threshold. And it's one of the questions that we wanted to look at as part of this project. In some cases, that washover can actually be beneficial. Particularly on much more southern nests where you've got really high temperatures and therefore really high female hatchling production, that wave washover can help reduce the temperature and can help increase male production. A lot of females is great for population recovery, but you still need males in the population to do their part of the equation. So since there are some of these natural defenses, it's a threat that they've been dealing with for millions of years. Is wave washover a threat that we need to manage? It's a question that the morning volunteers, the general public, anybody involved with sea turtle management asks and get asked all the time. And it's not exactly a straightforward answer. So like I said, there's some natural losses that are to be expected. And because we're dealing with an endangered species, we want to make sure that we're not causing any undue harm, even if that management action is well-intentioned. For example, a common management strategy is to relocate nests closer to the dune toe to try to reduce that risk of wave exposure. Well, those relocated nests may have different incubating conditions than they would have normally, where you may increase risks of hyperthermia, of disorientation, of nest desiccation, of predation of the nest. So you may be introducing some other risk factors, even though you're trying to be well-intentioned, and there's no guarantee that the nest in its original location would have washed away in the first place. So we want to make sure that we're being cautious about what management approaches we're considering, what all of the impacts are of each of our decisions. So as part of that, there's a number of questions that we need to answer before we can really go forward with some of our management decisions. That includes, where is wave exposure impacting the most nests? At what frequency or duration does wave exposure cause significant harm? Do these thresholds vary with developmental stage of the embryo, species, or population? What are the benefits of non-lethal exposure? Would relocating nests introduce other threats? And what other options are available besides relocation? So over the last 2 years, we took a crack at the first 3 of these questions. So if we're trying to get a sense of where waves are impacting the most nests, there's definitely a huge data set available from FWC that tracking all of the statewide nesting. So we took a look at 40 nesting beaches based in the Florida Panhandle, stretching from 2016 to 2019. Morning crews, both volunteer and professional, will go out each morning looking during the nesting season to look for new crawls, new nests, any exposure from waves or predation, poaching, all that sort of stuff, to see how the nests are incubating. And then once the nests hatch, they go in and they'll dig out the nest, count how many eggs were laid, how many hatched, give us some of that production information. So we have on one hand our sea turtle data set. On the other hand, we used wave height and wave period, and then tide height data from local NOAA buoys and tide gauges, and fed that into a wave run-up model to map out wave exposure across the entire Panhandle. Combining these two data sets, we can now look at what beaches have the highest nesting frequency, what beaches have the highest wave exposure, and how do those areas overlap, so we can identify some priority beaches to start moving forward with management and research questions. If you guys want to really dig into the methodology of that prioritization, the paper here was published last year, excuse me, open access in remote sensing. I'd encourage you to check it out. So when we take a look at these two data sets, we notice that nesting is concentrated in the eastern Panhandle. St. George Island, Little St. George, St. Joe Peninsula and State Park, and the St. Vincent National Wildlife Refuge were our top 5 beaches in terms of nesting frequency. Combined, these nests account for almost half of the nesting in the entire Florida Panhandle. So from 2016 to 2019, we have almost 6,800 nests available to us for our analysis. 42% of these nests reported wave washover. Now, this is washover that the morning crews noted. This is not coming from the model. This is what they've actually shown on the beach. So of those nests that were washed over, hatching success, which is the number of hatched eggs divided by the total clutch size, for those washover nests was reduced to about 27% compared to 78% for undisturbed nests. When we look at emergent success, this is the number of hatchlings that actually make it out of the nest compared to the clutch size. That drops to 25% versus 76% for our undisturbed nests. So we have a pretty significant drop in hatchling production in our nests when they get washed over. Included in that 42% of wave washover are 18% of the nests that reported complete or partial erosion. These are nests that are partially or completely lost to our wave exposure. When we look at our wave run-up model, it performed fairly well. We got an 89% accuracy in identifying washed over versus not washed over nests. On a day-to-day basis, wave exposure is a very low risk to nests incubating in the northern Gulf of Mexico. Only 12% of our daily total water level observations from throughout 2016 to 2019 impacted the nesting area. But storms are another question, another topic, that even though on a day-to-day basis, the threat is very low, when we get tropical storms and hurricanes, we impact a huge area of the beach, impacts on average about 50% of the available beach area throughout the Panhandle. And that includes 34% of nesting locations. Now, this is because turtles tend to nest above the high tide line. They're trying to get closer to the dunes. So as much as they may lose some of the available area, fewer nests are impacted than compared to just overall beach area. But 34% is still not, an insignificant number. Okay. So when we start looking at our beach priorities, when we're starting to rank those overlaps between nesting frequency and wave exposure, our top 5 beaches, our highest priority beaches, were the St. Joe State Park, St. Joseph Peninsula itself, St. George Island, Cape San Blas, excuse me, and Little St. George. You can see the average number of nests at risk for each of those nesting beaches based on this analysis. One of the interesting things that we noted when we were looking at these rankings is that even though all 5 of these beaches are in the top quartile for nesting frequency, only St. Joe State Park and Cape San Blas were also in the top quartile for wave exposure. St. George and Little St. George were in the bottom quartile of wave exposure. They had the lowest 25% of wave exposed nests. However, because their nesting frequency is so high, even that low proportion of exposure meant that they still had a significant number of nests, a significant count of nests that were exposed, hence their listing in this ranking. But that leads us to an interesting question that was in one of our to-do list of 7 questions, was how do we manage this threat then? Well, areas of low exposure like St. George and Little St. George may be better to protect as refugia. They have a lot of available beach area, a few low proportion nests that are exposed. There's areas for these turtles to migrate inland to reduce that threat. And so it may be better for us to just protect these areas as is, compared to places like the St. Joe State Park or Cape San Blas, where you have a high proportion of nest exposed and a high frequency of nesting. Those areas may be better primed for us for intervention as we try to answer some of these other research questions to determine if that's really the best strategy moving forward. So now that we have a sense of where wave exposure is happening most often, we wanted to take a look at the next 2 questions, which are: at what frequency or duration does wave exposure cause significant harm? And do these thresholds vary with developmental stage of the embryo, species, or population? So to do this, we focused on St. George Island during last year's nesting season. St. George, as you guys will remember from the previous slides, is the highest frequency nesting in the Panhandle and was ranked number 3 on our priority list. And it's just a beautiful place to work. It's easily accessible, so what more could you want from a field site? So we worked with the morning crews on St. George Island to take a look at the nesting location, wave exposure, and hatchling production per their normal protocol. This gives us a data set across the entire island. It gives us a much larger number of nests to work with, but we lose some temporal resolution because the morning surveys are conducted once a day. On a second prong of this project, we took a subset of those nests. We took 16 nests from throughout the island and installed hobo water level loggers to give us an hourly look at what the water table is doing. So this gives us a much higher temporal resolution look at what's going on for these nests, but it's a much smaller subset. We've lost sample size due to just the increased logistics and costs for monitoring those nests. These are all based on methods that I developed as part of my PhD working out in Alabama. So if you guys are interested in following up on those methods, I'd encourage you to check out the papers listed at the bottom of the slide. So when we take a look at this last nesting season, Tropical Storm Fred did an absolute number on St. George this year. We had 252 nests laid on the beach, 230 loggerhead, 22 green. 76.6% of them reported wave exposure at any point during their incubation. 42% were completely or partially eroded. This is a huge number of nests lost that almost exclusively from Tropical Storm Fred. Like I said, it really did a number on us. By comparison, only about 17% of the nests were predated. And this was largely by ghost crabs, so you lose a couple eggs throughout the incubation. Only 1 nest was predated by fire ants. Nothing from coyotes or anything larger than a ghost crab. When we take a look at that wave exposure frequency, we see a pretty drastic reduction going from 0 to our first washover. We've dropped from about 90% hatching success with no inundation to down to about 40% after our first washover. As we continue to increase that washover frequency, we drop down to about 25% after 2 washovers and basically 0 after 3. When we look at the timing of that wave exposure, the timing was largely irrelevant. These are all nests that were only washed over once, so we don't have any confounding effects with multiple washovers. But if we notice, throughout that 2-month incubation, it really didn't matter in terms of hatching success or emergent success if that inundation occurred, a week after the nest was laid or right before the nest hatched. Now the exception here, and I didn't include it because it's only a handful of nests, but something that we've seen on the beach was that you can see a high hatching success but low emergent success if the wave washover occurs after the eggs have hatched, but before the hatchlings have actually emerged from the nest. It takes the hatchlings several days to crawl out of their egg chamber and get up to the surface. At this point, they are, exchanging oxygen and carbon dioxide with the surrounding sand environment. If you get wave washover during that time, the hatchlings can drown in the nest. So you can get this difference between hatching success and emergent success. But like I said, I didn't include it in this plot just because it's only a couple nests, but it is something that we've seen and that morning crews have reported as their, as their experience increases. For our hobo loggers, we only had 7 of the 16 deployed actually survive, again, thanks to Tropical Storm Fred. So I've combined our St. George data set with data from 2017 and 2018 from Loggerhead nests on the Fort Morgan Peninsula of Alabama. These turtles are part of the same genetic subunit, and the hobo loggers were deployed with the same methodology. So this bumped our sample size up to 28 available nests between 2017 and 2021. When we start looking at the inundation duration, how long these nests were underwater, we start noticing a drop to 0 hatchling success at about 20 hours of cumulative inundation exposure. But there's a lot of variability in this data. All right, so where do we go from here? Throughout the last 2 years with these 2 different projects, we've demonstrated that wave exposure is most problematic in the Eastern Panhandle, that hatchling production stops at about 3 or more washovers or 20 hours or more of cumulative inundation, and that the timing of that washover had little effect. However, using these data sets, there's still a lot of variability in hatchling production that these models are not accounting for. So we need larger data sets to see what may be going on, but also there may be some interactions between, say, the duration of one exposure and what percentage of the nest was inundated at any one time. So that's a lot of the data that the hobo loggers can help us answer. So as we build up that data set, we can hopefully explain a lot more of that variability and how some of these factors may be interacting with each other. This is also just a look at our population up here in the Northern Gulf. So we still need to take a look at how these exposure thresholds may change by species or by different populations. We still need to look at what are the benefits of non-lethal exposure in terms of increased male production, increased crawling speeds, better fitness, different things like that. And then what are the various management options available to us, whether that's nest relocation, beach conservation, or any action in between. So thank you all for your time. If you have any questions, I'd be happy to answer them, or you can reach out to me at my email there at mw15w@my.fsu.edu. Thank you guys for listening.
Thank you very much, Matt. I have a question for you, but I'm going to look and see if there are any questions from the audience first.
Mm-hmm.
And Anita, Kennedy, you guys jump in if you see one. If anyone's hands go up. So while we're letting folks come off mute or ask their question, my question has to do with the fact that the difference between Franklin County beaches and Gulf County beaches is the beach renourishment programs or projects. And I was curious if you factored that into your work, either previous renourishment projects or that is a potential strategy to reduce wave washover.
Mm-hmm. So when we're building these wave models, we used beach elevations based on LiDAR surveys from 1998 to 2018, if I remember, or 2020, I forget exactly what the latest cutoff was. And so we used 20 years of available surveys to basically design what does the average beach look like, what is the average elevation. So that included times when some of these beaches may have been incredibly eroded or after certain renourishment projects, but we kind of got in what does the average beach look like when we're running these models. So there is going to be some variability when we look at what is the what does the real beach look like compared to this model beach. But we've noticed the model does pretty well in identifying these kind of high risk areas. If we have a new elevation survey, whether that's from a LiDAR survey or any sort of ground measurements, we can rerun these models with what the beach looks like today and get a better estimate of which nests or locations are most at risk. So we can update this model with new data, say after a beach renourishment project, so we can see how that risk has changed. When it comes to the use of beach renourishment itself to reduce wave washover, obviously it's great that we're building the beach back out. We've got a lot more nesting area available, but we have to be careful about what how that, I'm trying to remember the correct term for it, but basically what that profile looks like. The profile that's generally most resilient to wave erosion is not always the best profile for turtles to be crawling up. The material that gets used, how much that sand gets compacted. When you take a look at the literature, it's really kind of 50-50 on the value of beach renourishment. In some places it's done great. The turtles really love it. They've got high productivity, all's good. Other places you see a couple of years of really low nesting success. The turtles crawl up and say, nah, I don't like this, and leave. So there may be some better options in terms of how we put those renourishment projects in, because those projects aren't going away. We want to keep tourism coming. We want to protect that upland development. So we need to figure out a way to make sure that renourishment is done in a way that keeps the turtles happy as well.
Thank you. Thank you. I see there's a question from Amanda Smith. Amanda, you want to come off mute and ask your question?
Amanda, you're currently muted. You may want to
okay, sorry. Sorry about that, everybody. Hey, I just had a quick question regarding your slide back showing all the maps of the priority categories. I wanted to see on the very bottom, you had a very high frequency maps showing only a portion of the maps previous to that, and I didn't know if you had data for that, and also like would that affect your modeling, your outcome?
Yeah, Kennedy, I can't seem to control the PowerPoint. Would you mind bringing that slide up? There we go. All right, so you're talking about this one?
Yes.
All right. Yeah, so working through this graphic, that top panel is going to be our nesting frequency. So you can see where our highest frequency nests are in the eastern panhandle. We look at the proportion of nests exposed to waves. It's still concentrated in the eastern panhandle, but it's much more spatially variable. So when we combine these two, we had our priority categories that showed, again, the eastern panhandle where most of our nests are being exposed. This bottom panel is highlighting that difference between areas that were high frequency of nesting and high frequency of wave exposure, or high proportion of wave exposure, and then those that were high frequency nesting but low proportion of wave exposure. So this was showing Cape Sand Glass on the bottom, and then St. Joe State Park, looking up further up the peninsula there as those areas of both high frequency wave exposure and nesting, and then showing Little St. George and St. George Island as areas where we have a lot of nesting but a low proportion of wave exposure to help differentiate those. They're still all high priority locations, but it was just in there to help show that there's a dichotomy here when we start looking at wave exposure in particular and how that influences our management decisions.
Okay, thank you. I was just curious about the very bottom because I didn't see St. Vincent or Eastern St. George on there, but thank you for explaining. I must have missed that.
Yeah, so the state park is considered its own nesting beach. separate from the rest of St. George, which is why that eastern portion of the island itself isn't included on here. It's the same thing where the state park on St. Joe is considered separately from the rest of the peninsula.
Okay. Okay, thank you.
Yep, you didn't miss it. I just didn't go through the whole breakdown of the graphic. That was on me.
Thank you so much, Matt. Again, that was a great talk. And we're going to transition to our next speaker, Megan Lamb. And this is going to be a great continuation of the discussion. Megan is in our research section here at the Research Reserve. And this morning, the title of her talk is Sea Turtle Incubation Patterns in the Northern Gulf of Mexico. So Megan, if you're ready, I see you. I hear you. I hear you. Take it away. Thank you.
Great. Thanks for that introduction, Jenna. As Jenna mentioned, I'm a biologist here in the research section at the Apalachicola NERR, and Matt did indeed give me a great introduction. I'm going to be continuing some of the themes from his talk and talk about a little more about our sandy beaches serving as incubators for sea turtle nests. I'm going to be focusing on the temperature characteristics of our sandy beaches. So the incubation temperature of sea turtles plays a critical role in a lot of the developmental processes. So development of sea turtle nests is temperature dependent. So warmer nests will incubate faster than cooler nests. Temperature influences the overall success of a nest. Sea turtle nests incubate between about 24 to 35 degrees Celsius. And if they get too far out of those temperature zones, it can cause a nest failure. The temperature of incubation also can influence the fitness of the hatchlings themselves. And finally, nest temperatures determine the sex ratios that are produced by the nest. So the temperature at which a nest incubates actually determines if hatchlings are male or female. And this is called temperature-dependent sex determination. So it's not actually the temperatures throughout the entire incubation that determines sex. There's a period called the thermosensitive period. These are the stages of development when that determination occurs, and it corresponds roughly with the middle stages of development. And keep in mind that since development is temperature dependent, varying incubation temperatures throughout the incubation period may shift when that thermosensitive period is occurring. And there's a global concern that with warming temperatures, sea turtle populations may be becoming feminized. And as Matt noted, in the short term, more females may help nesting populations, but we do need males to continue the population. And the thermal nesting environment in the northern Gulf of Mexico is historically not well studied. So we really don't have a great idea of what's going on in our local nesting beaches. So this figure on the right of this slide oops, I'm forgetting, sorry about that. I am forgetting to change my slides. Sorry about that. So this figure on the right, it represents the temperature-dependent sex determination curve of sea turtles. So I have a pointer. There's this central point in the middle called the pivotal temperature, PT, and this is where a 1-to-1 ratio of males to females is produced. As temperatures get cooler, more and more males are produced until only males are produced, and as temperatures get warmer, more and more females are produced until only females are produced. And this range of temperatures that produces mixed sex ratios represented by the gray box is called the transitional range of temperatures, TRT. So the PT and TRTs can vary by turtle species and can also vary by population within the same species. So different nesting populations may have different characteristics. So the numbers that I show on this slide are show a pivotal temperature of 29.48 degrees Celsius and lower and upper TRT limits of 27.8 and 31.2. So these numbers I borrowed from a close by population of loggerhead sea turtles nesting on the Atlantic coast. And this is these are the PT and TRTs that I'll be referring to throughout the talk. Okay. Oops. Oh. Sorry, having a little trouble with my slide forwarding. Okay, so to start off the project, so since the northern Gulf of Mexico is rather understudied, I started with some pretty broad study objectives. I wanted to create a temperature profile of the Little St. George Island nesting beach. I wanted to provide baseline data of nest incubation temperatures for the genetically distinct northern Gulf of Mexico loggerhead population and provide insight into the sex ratios of hatchlings being produced. And finally, I wanted to look at metabolic heating. Egg clutches actually produce their own heat during incubation, which is called metabolic heat. And I wanted to quantify this. And my hope is that understanding the beach thermal environment coupled with better understanding of the amount of metabolic heat occurring could allow for a less invasive way to predict the incubation temperatures experienced by nests. So my study site is Little St. George Island. It's a 15-kilometer long, undeveloped subtropical barrier island bounding the Apalachicola Bay. Loggerhead sea turtles that nest here are part of the Northwest Atlantic loggerhead population, and the northern Gulf of Mexico hosts a genetically distinct subunit. There's an average of about 130 loggerhead nests yearly on this island, and loggerheads are the most common sea turtle nesting species in the Panhandle. And nesting season runs roughly May to October. So to create a thermal profile of the nesting beach, I buried temperature loggers and transects from the primary dune line, dune crest, to just above the water line, spaced 8 meters apart, and at a depth of 45 centimeters, which is the mid-clutch depth on this beach. The number of transect locations varied. I started in 2016 with only 1 location and lost a lot of data due to washover that year. But then for the rest of the study period, I had 3 to 6 locations. And then to look at incubation temperatures, I located nests the morning after they were laid, carefully placed a temperature logger in the middle of the clutch. I tried to include nests that were laid in the early, middle, and late parts of the nesting season, so to represent the entire nesting season and also different geographical areas of the beach. And then after loggers were installed, the nests were marked, monitored for disturbances, and then after emergence, hatching success evaluations were conducted. I don't want to go into too many details about data treatment due to time constraints, but I did take my incubation temperature data and I ran it through a model that was developed by Gerondo et al., published in 2018, to determine when the thermosensitive period occurred during each nest's incubation and predict sex ratios. And then finally, to measure the metabolic heating, I installed a second temperature logger to the side of each study nest at the same depth as the clutch logger. So subtracting that sand temperature from the nest temperature gives us the metabolic heating produced by a nest. And I only am including nests that experience some percentage of successful development in the results here. Okay, so this figure shows the daily mean sand temperatures by year measured on Little St. George Island. It's a lot of information compressed into one figure. The transect locations are combined for each year, and the positions on the beach from the dune to above the mean high water line are shown with the different types of lines, different dotting and dashing. The shading around each line represents a 95% confidence interval. Since so little data was collected in 2016, I didn't include it here, and there's data missing at the end of 2018 because of Hurricane Michael. So in this figure, the solid red horizontal line represents that pivotal temperature of 29.48 degrees, and the red dashed lines represent the upper and lower bounds of the transitional range of temperatures, which produces mixed ratios of males and females. So going forward throughout the talk, the solid and dashed red lines in all figures will represent the pivotal temperature and bounds of the TRT. So sand temperatures in all years, as you can see, fall within the transitional range of temperatures for much of the nesting season. You can see that July and August are the warmest months each year. September 2019 was also unusually warm. So a multi-way ANOVA showed statistical support for these observations. I tested to see if year, month, and distance to dune were predictors for significant differences in temperature, and they all were. To try to just be brief with the results, all years were different except 2018 and 2020 were similar. July and August were statistically similar, and all other months were different from each other. And then the position at 0 meters to the dune, which is the top of the primary dune line, was different from most others. It grouped often with the next position 8 meters from the dune, which roughly corresponds with the toe of the dune. And additional positions further down the beach in the foreshore area all grouped together. And so this is the highest temperatures, the highest up on the beach were warmest. So that top of dune and toe of dune were the warmest, and then the foreshore area was cooler. So just looking at the big picture, sand temperature data is telling us that the beach at Loggerhead nest depth spends a large part of the nesting season in those transitional range of temperatures on Little St. George Island. So next we'll look at some nest incubation temperatures measured. So these nests represent just a few of the nests measured through the study. And the gray boxes indicate when the thermosensitive period occurred for each nest. So when that sex was being determined in that nest, or sex ratios. You can see that the nests experience a daily fluctuation in temperatures. There are some local weather events lasting a few days where you see larger drops and swings, maybe a couple rainy, cloudy periods, followed usually by a kind of recovery period. The temperatures come back up. And the nests on Little St. George Island might experience different patterns in temperature throughout incubation. So the nest on the upper left, you can see the temperature steadily increased throughout the incubation period. On the upper right and bottom left, you can see the overall trend the temperatures seem fairly steady throughout incubation, with a fewer larger drops and then corresponding increases due to weather events. And then on the bottom right, this nest here, the temperatures increase in the final third of incubation, but this is past the thermosensitive period. So this figure shows the mean incubation temperatures during the thermosensitive period of the 79 nests that I measured this for in the past 6 seasons. It's in chronological order, so 2016 at the top, all the way down to 2021 nests at the bottom. And we can see that from 2017 to 2020, most nests experienced a mean thermosensitive temperature between the pivotal temperature, once again represented by this solid red line, and the upper end of the transitional range of temperatures, so right along in here. In 2016 and 21, we saw some different patterns. The nests measured in 2016 were at or above that upper transitional range of temperature threshold. And in 2016, these early season nests, these nests laid in the early portion of the season, were at the lower end of the transitional range of temperatures. So next we'll look at what sex ratio predictions we can make based on these temperatures. And they kind of follow these, the temperatures that we saw. In 2017 to 2020, nests are predicted to have produced between 6.2 to 60.2% male. Many nests do show a female bias, but overall the nests are producing mixed sex ratios. And those hot 2016 nests measured would suggest very very few males were produced in 2016. And then that's up there. And then once again, these early 2021 nests produced almost entirely males. So next, I looked for statistical significant differences between the years or the part of nesting season that these nests were laid in. And so I did a two-way ANOVA to examine the effective year and part of season in which a nest was laid on the mean incubation temperature during the thermosensitive period. And year and part of season the nest was laid were both significant. There was a significant interaction term between the two. So I focused on the main effects of my analysis. 2016 and 2021 nests were statistically different than all the other years. We know we've already pointed out 2016 had those warm nests and 2021 had some cooler nests. And there were no significant differences between nests from 2017 to 2020. And then also early season nests were statistically different than both middle and later season nests. And I think that statistic is really being driven by those early season 2021 nests. Finally, we'll look at metabolic heating and where that comes into play, thinking of the relationship between the sand temperatures and clutch temperatures. So this figure shows the same nest incubation temps we looked at a few slides ago. And the sand temperature is now added. It's represented by the dashed orange line. The difference between the clutch temperature and sand temperature is the amount of metabolic heat that a nest is producing. And as you can see, in the early part of incubation, nest and sand temperatures are very similar. There's not a lot of metabolic heat occurring at that point during development, but the metabolic heat begins increasing about halfway through the incubation period and is greatest at the end of incubation, can be 2 to 3 degrees at the end of the incubation period. But at that point, the embryo has already passed its thermosensitive stages. So if we're interested in how metabolic heat will affect sex ratios, we want to focus on the thermosensitive period. But the average, the average temperature up here on the right, throughout the entire incubation, the amount of metabolic heating is pretty similar to the average going on during that thermosensitive period. So during the thermosensitive period, about 0.72 degrees of metabolic heating is occurring, so a little under 1 degree. And if you look at the nest on the upper right here, you'll see that this example doesn't show much of a difference between the clutch and sand temperatures. So that nest had a very low hatch success percentage of 6%. And that observation really hones in on what's driving the production of metabolic heat. I'm almost done, Jenna. Which is clutch size and the hatch success percentage. So this makes a lot of sense because each developing egg is what's producing metabolic heat that contributes to overall heating. So in quick summary, the beach thermal profile suggests sand temperatures on Little St. George for much of the nesting season are within that transitional range of temperatures. Incubation temperatures and predicted sex ratios also suggest Little St. George nests are producing mixed sex ratios. There's variation between years and sometimes within seasons. Metabolic heating during that thermosensitive period is less than 1 degree, and it's related to clutch size and hatching success percentages. There are some limitations to this type of analysis. Sample size for the incubation temperature is a bit small for some years or parts of seasons. Mother Nature just doesn't always cooperate. But this type of analysis and the model doesn't account for the effects of soil moisture or the variance of temperature. I talk a lot about mean temperatures, but variance may also influence sex ratios. The relationship is just not well understood at this point. And of course, the pivotal temperature and transitional range of temperatures are not studied specifically for the northern Gulf of Mexico loggerheads. So I use that Atlantic coast population as a proxy. But these results really show the importance of long-term studies And, you know, this is a zoom in on one nesting beach. It's an important nesting beach for the northern Gulf of Mexico. But if we want to make predictions about larger populations, we really need to look at the nesting unit as a whole. So we need more data from around the northern Gulf of Mexico. So I know I'm out of time, so I want to thank these people for the money and the help with fieldwork. And if I don't have time for questions now, you could email me or I'll check the Padlet also. And thank you for your attention.
No, that was great, Megan. Thank you so much. And yeah, because we're a couple minutes off schedule, and I don't think I see any hands up in the attendee list. Yes, please visit the Padlet, shoot Megan an email or make a comment, and connect with her there. Thank you, Megan.
Thanks.
All right, we're going to shift to our next presenter, Jim Cox from the Tall Timbers Research Station. And the name of Jim's talk is NOAA Firebird, Fire Effects on Secretive Marsh Birds in the Gulf of Mexico Marshes. So Jim, if you're ready to take over.
I'm ready. Can you hear me?
I can hear you. Take it away.
Hey, thanks for the invitation to speak. I'm enjoying some of the symposium and all the great information being provided about the important Apalachicola Basin. And it's kind of new for us at Tall Timbers. You know, we got our start over 100 years ago looking at the effects of fire. And we've got this new project now called the Firebird project, where we're looking at fire in coastal settings. I'm going to give you kind of a quick overview of some of the species of concern here and what we're looking at, and hope to come back over the years and, you know, provide you with updates. And I have two great people, Heather Levy and Heather Hill, that are helping me on this project, and really deserve all the credit for the great data that we've been able to collect. This project, let's try advancing. This project extends over 5 states, 5 Gulf states we have here, and has actually 25 collaborators, and is very large. We're looking at these issues across the entire Gulf Coast region for these rare species we're dealing with. Most of the focus, though, is in Texas and Florida, where the highest concentrations of some of the marshes we're interested in occur. But just to let you know, this is a very extensive program that extends well beyond the borders of Florida for sure. Our study areas have been primarily in the Big Bend region, but extend out west to St. Vincent and St. George. And we're also looking at some of the issues down as far south as near Tampa, where we have mangrove encroachment taking in place in a lot of the coastal marshes that we're concerned about, and are trying to figure out how fire management can help manage these areas for the rare species we're dealing with. We're talking about the areas we're looking at. It is the high marsh area, the irregularly inundated portion of the marsh, uphill from all the other things that are down to hit by the high tide and low tide areas. These areas are, you know, only once in a while are they inundated, except as, you know, sea level rise continues, it's going to happen more often. A lot of the species of concern is Disticulus. You have 2 or 3 different species of Spartina, not Spartina alterniflora, but patens, and Spartini, and also the Bakeri versions, several sedges and everything. But these are really grass-dominated settings, and an area where they contain a lot of very fire-friendly fuels that can carry fires, and also these areas are really important to a group of rare species. Fire came through these areas very regularly, you know, moving out of the upland pines. Fire has been a dominating force in Florida for over 20,000 years, and we know a lot about how fire effects occur in the upland pines, but we know less about their effects in these lower areas down closer to the coast, other than we know that it came with there some regularity moving in and out of the pine woods. Based on the data we have for the upland systems, fires in Florida dating back to the 1500s came through about once every 2 to 5 years, with about 75% of them coming through about at 3 years or more frequently. So it's a very regular and very important form of disturbance. They're not crown killing fires. They don't kill the trees. They're very low intensity fires that move around and basically give the ground cover a haircut. Things resprout and recondition themselves quickly after the fire. But just to distinguish it from the high intensity fire, these are very low intensity fires we have moving through the area. This shows a site on St. George Island that hasn't been burned in probably 5 or 6 years. And you can see one of the areas of what happens when you don't have fire in an area. You can see the various saltbush and all these shrubby hardwoods starting to encroach in the area. These would be killed off by the fire and removed, but over time, these can come established and dominate an area. And this is really moving from a grassland to a move of shrubby and brushy conditions that aren't suitable for some of the rare species that occur in these high marsh areas. We don't know much about the interval needed for these systems for sure. There hasn't been much study. We have some recommendations for up on the North Atlantic coast of 1 to 4 year return intervals. Some recommendations from Louisiana to allow for 2 growing seasons to occur before you apply fire back in the region. But we really don't have a lot of data for the rest of the Gulf Coast, and that's one of the things we're trying to obtain as part of this work. A key focus for us is this curious beast, the eastern black rail. It's about the size of a small rat, and it acts like a rat. It's a very elusive animal that scurries around at ground level, rarely flies, and is really one of the most sought after birds by birders in North America because it is so hard to see and to study. Unfortunately, it's also undertaken a very pronounced decline in recent years, an estimated greater than 85% decline throughout its range, and it was listed as a threatened species back in October of 2020. And so it's increasingly of great importance in trying to figure out how to manage for this bird and prevent these declines from becoming even more severe. The Gulf Coast has a pretty large population. The bird also occurs inland in California and also occurs down into South America. But the eastern black rail, the one that we have here, is estimated along the Gulf Coast to contain about 800 to 2,400 individuals. Other places in Florida have large populations of the Everglades, and also the Atlantic coast has a very large population as well too. So how do we manage? On the lower right, you can see a fire moving through an area, and you can see all the shrubby brush that's there. This place will become more suitable for rails if those shrubs are removed. But how do we manage fire for this very elusive and very small animal that likes to spend all its time on the ground? Carefully. But this it really requires fire. This is some data from over in Louisiana showing the percentage of Spartini in relation to whether or not a rail inhabits a patch. And you can see the striking relationship there. The more you have these grasses, the more chances you have of the rails occurring there. And the more the area supports shrubs and stuff, the less chance you have of having rails occupy the site. One thing we've got to remember with the black rails is that fires can be harmful to the animal. This, again, is a very cryptic species that stays at ground level. It really doesn't like to fly very much. It likes to try to evade danger by running away. And we've had some very bad fires that have affected the rail populations elsewhere in the country. One of the more notable ones is this fire that occurred over at St. John's National Wildlife Refuge back in the 1990s, where there was a kill of 40 black rails documented in this fire. They were burning that large section of marsh there. You can see in the center that has all the cross sections of roads and stuff that have broken out. But there's a lot to be learned from this fire and applying how we might use fire for managing rail habitat elsewhere where the animal occurs. One of the things that happened in this fire was it was a great rush. They basically started igniting the area about 3 p.m. in the afternoon, and they were finished igniting it by 5 p.m. And they were using aerial ignition patterns, which create these, they drop ping pong balls from helicopters that explode and launch the fire. And you can see the crazy complex convergence patterns that this particular type of fire creates. All these fires are going to be merging together and closing in. And sometimes when you have a species like black rail that prefers to run rather than fly, this can be very deleterious to the animal. So this is not like the natural fire systems where a point ignition would start it and the fire would have moved in a sort of meandering pattern over a very large area and probably more slowly. The other thing to consider about black rails is there's a period in their life annual cycle, roughly from August, September, when they're flightless. The birds undergo a molt at this point, and they molt all of their flight feathers and are basically stuck on the ground with no wing power, if you will, to carry them away should a fire occur in this particular part of the annual cycle. The other thing about this fire that's probably also detrimental is that they after they completed the fire and had it mostly burned out, they went back afterwards and they applied fire again to all the unburned patches. This is a common practice that a lot of land managers sometimes do. they really don't like to see those patches sometimes, even though we know naturally when a natural fire came through, patches were invariably part of the mix of the outcome of any fire. But this particular time, they went back in and reignited some of those patches that hadn't burned up when they were doing the more complete fire. This is unfortunate. This is the sort of patches that you can see on some fires that where it's more patchy. This shows a recent shire fire at St. Vincent National Wildlife Refuge, and you can see that wonderful little patch of juncus there that didn't burn up there in the midst of all the bulrush here. Those are the types of areas that these black rails like to move into and see to avoid the fire, usually lower lying areas that have a little bit of water in them. And this sort of patch is really important for black rail management, is to make sure the fires have this sort of patchy network of undisturbed areas in the mix of other areas that burn more thoroughly. The other thing I'd like to point out in this slide is just the flowering response of the bulrush here. One of the important things that fire does is recycle nutrients, and there's this big pulse of calcium and phosphorus that occurs after burn that we can even show that has some effect on the clutch sizes that birds lay. The immediate pulse of new nutrients that have been tied up in plants coming out and entering the system again has a very big impact on productivity, both for the plants and for the birds. So patchiness is very important. We don't know the interval yet. Is it every 2 years, every 4 years? Intensity, ignition we know about. You probably shouldn't do those aerial ignitions unless you've got a lot of distance in between the ping pong balls that you're dropping. And basically we've got a lot to learn from this burn at St. John's. This again shows Mallard Slough on St. Vincent National Wildlife Refuge. This shows again the patchiness of that burn. You can see the juncus that didn't burn next to the bulrush that did. And we're going to be quantifying a patchiness using some aerial photography, satellite imagery, and we hope to get at this issue and help to be able to define what we mean by patchiness suitable for rail. We do this, our geospatial lab here at Tall Timbers has developed these wonderful tools for taking imagery before and after burn and calculating what's called the burn index for the area. This shows a fire on St. Mark's. The A picture was taken about 8 months before the fire. The F picture was taken about 3 months after the fire occurred, and they can calculate this index based on the change in the spectral reflectance from the sites. This shows in the process data for St. Vincent's based on the burn that they did last year in fall. You can see the bright red areas are the ones that burn very thoroughly and graded into the gray areas which didn't burn as hot, and into the other unshaded areas there which didn't burn at all. And you can see the rails kind of clustering around where the interface between burned and unburned vegetation occurs. But this tool will allow us to look at fires once they are applied and calculate the patchiness indices for these areas, and then follow up what happens to the rails afterwards. We also did a thorough survey throughout the Big Bend coast this past year with Heather Hill shown here and Heather Levy doing most of the work. And we can look at some of the sites where we found rails. This was a labor of love. We were asked to visit 147 sites 6 times. Basically starting pre-dawn. For this particular bird, you have to get out before the sun comes up, and you have to do it after the sun goes down. And you're basically listening for the bird's call, which I'll give you a little example of right here. Here's what the birds sound like and what is music to our ears when we're out in the field. That's the famous kiki-doo call. I heard my first bird after about a month of surveying, so we thought we weren't going to find any birds, but we found out that they do call, and we just were sampling a little too early for some of this work. Anyway, the results were that this study area was again from Tampa up to St. Vincent's, doing these playbacks on the areas where we hope to find rails. Basically, here shows some results from St. Mark's National Wildlife Refuge, where we detected rails and plotted their potential occurrence based on their calls. I'd just like to point out this area had been burned about 3 months earlier before these surveys were conducted, and was chock full of responding rails. We don't know the exact number of rails, but it seemed to be well occupied by at least 2 or 3 individuals. And again, may reflect a preference that this bird has for areas that are recently burned as far as breeding habitat goes. Again, the other important note from this particular survey is that you shouldn't be out in March trying to do these playbacks for rails because they don't respond there. The peak of the nesting season is June, and so really the time to really focus your efforts is from mid-April through July for black rails. Another important species that we'll be looking at too is the seaside sparrow. This is the one that we have here in our area, is the Wakulla seaside sparrow. It's a cousin of the dusky seaside sparrow that's now extinct. It's another common species found in the coastal marshes of the area. We have a little bit of information again from Mallard Slough at St. Vincent's, where they have religiously, until recently, been burning half the marsh each year. Back in the late 1970s, there was a study conducted of the seaside sparrow on St. Vincent, basically doing counts in the areas that had been burned the previous year versus the one that had been burned 2 years earlier. And here's some of the data. The first year post-burn, shown in blue, had higher counts throughout all the surveys conducted compared to the second year post-burn. And this bird seems to respond very positively to fire and moves into an area after it's burned. You may wonder why this is, but you kind of have to take the perspective of these birds that spend their lives on the ground foraging for food. As that vegetation begins to accumulate over time after the fire has come through, it can actually clog up the ground cover pretty severely, and it gets really clogged up with debris, overgrown vegetation. And during that first year after burn, the ground cover is much more open, and you can forage around much easier, and you can find food and items that have dropped to the ground more easily during that first year following the fire. Another species we're looking at is LeConte sea sparrow, which is a migrant that comes into our area in winter. This is another one found in our coastal marshes. Based on some work in Texas, as you can see in the upper left-hand corner, the LeConte sparrow seems to come into an area of really more in greater abundance 2 years after fire. But this is kind of contrary to some of our results from this past year. We have been sampling St. Vincent, for example, on a fire that came through in fall of 2021, and this year in winter, we had some of the highest contents of LeConte sparrow there just 6 months after the fire had come through back last year. So we might find some new information about the response of these overwintering species to the use of fire. Again, St. Vincent's, you can see here again the mix of vegetation that burned and did not burn, and this is really important for all of these species, having access to cover when fire comes through in every area, and not having to move, but also having new vegetation coming along after the fire has come through, resprouting and providing a lush, new productive setting. One of the other tools that will be important and may be of interest to the group here is we are trying to map the high marsh areas throughout the Gulf Coast. This is being done by people at Mississippi State University. This is an important ecotone for rare plants and other animals, and also for animals. And basically, we're doing this using basically imagery and also a lot of information on tides and the potential soils underlying these conditions. And we're at version 2.1 right now at this point, but it's looking pretty good. We'll have a map of the high marsh areas where we perhaps should be focusing some of our future sampling efforts. The other helpful thing that we're working with too are autonomous recording units. Surveying for these birds is not easy, but these units can sit out there patiently and record the environmental sound. Here are the two heathers. We call them the taller heather and the shorter heather. We've done much of this work. And these units are recording out there while we're collecting information as well, but they can sit out there patiently waiting for the wind to die down, waiting for conditions to be just right for the birds to call. Importantly, we now have a new tool for analyzing these data. One of the worst things about these particular types of data collection is you end up with several terabytes of recordings. It's almost impossible for a person to go through. But we now have an automated way to go through these data files using a Cornell program, BirdNet. We can basically upload our files, pay them a small fund amount to analyze them, and have the recordings of the black rails pegged and these other species within the files. We have to go back and verify, but this is going to be a wonderful savings of time and provide reliable information on a broad species over a much broader area. This shows the Kikidoo spectrogram, and basically these systems look at these and compare to all the possibilities that they might be, and they peg black rail, can distinguish it from other species pretty readily. How well it works is shown in this graph. We have the manual review shown on the y-axis compared with the BirdNet score on the x-axis. And as you see, as the BirdNet gives you a higher probability. More often than not, it's a black rail calling, and this costs 65 cents per hour. So that's it. Here's the information on the project and my email address if you have questions, and I'll be happy to try to answer any questions right now that there might be.
Thank you so much, Jim. And yeah, we're running a couple minutes behind, but I would like to invite the audience, if anyone has a question, we'll go ahead and put Jim on the spot. And let me scan through, see if I see any. I was going to mention that, okay, so someone asked if Jim could show the blue kickadoo again.
Play it, or
I think just show.
if you can, if Kennedy can go up a couple of slides.
Or kickadoo is the sound, but the.
Right. And here it's down one from there, I think. Okay, and here the kickadoo, the dark spectrums that you see about dispersed 4 copies of it there, that is the kickadoo call of the black rail. This shows the frequency and kilohertz, and basically this system can analyze the spacing, the volume, the kilohertz, and everything. That's what the Cornell is looking at, and taking all this digital data, and they using artificial intelligence to identify this as a black rail versus some other bird that might be calling out there.
Awesome, thank you. I was just going to mention that, so later after the break, we have Renee Collini, who's going to talk about sea level rise projections for the Northern Gulf and the Big Bend area. And she's coordinating on several different projects looking at marsh mapping, looking at what's the correct term? Ground truthing LiDAR data. So looking at high marsh, low marsh. And then also working with the HydroMem group that's linking marsh productivity with sea level rise models. So she's got a lot going on that's gonna maybe inform how these areas change over the next several years. So hopefully you're connecting with the group, and you know, that can maybe inform your research.
Oh, sure. I'll look forward to the presentation, and also quickly jot down the name and contact her about some of our efforts here. Most of our stuff is being done by Mississippi State University, and but we can share the products with anyone who's interested in looking at them.
It's so cool. Thank you very much, Jim. I appreciate it.
Sure.
Okay, we're going to transition over to Kira Allen. Kira is a graduate student at the University of Central Florida, and she is also our Margaret A. Davidson Fellow. This morning, her talk is going to be modeling the Apalachicola Bay food web, hydrodynamics, and implications of salinity changes. So Kira, we're starting about 5 minutes late. Hope that's okay, but don't sweat it. We'll get you done, okay? Take it away.
All right, thank you. Hi, everyone. I'm Kira Allen. I'm ANERR's Margaret A. Davidson Fellow, and I'm also a master's in biology student at University of Central Florida. My research for both my thesis and the Davidson Fellowship involves modeling how changing salinity regimes affect the Apalachicola Bay food web. And I presented at this symposium last year, and I gave a pretty brief introduction to the project then. So a lot of progress has been made since then. So today I'll be providing a more detailed update on the status of the project and the methods being used. See if I can get, okay, there we go. First, some background. My project is particularly interested in 2 major drivers of salinity changes in Apalachicola Bay. The first is freshwater reduction. Apalachicola River is the main source of freshwater to the bay. And I'm sure many of you are familiar with the Supreme Court legal battle over the Apalachicola Chattahoochee Flint, or ACF, river basin, which is shown in the map on the left there, that Apalachicola River is a part of. Georgia is looking to implement greater amounts of freshwater diversion upstream to support drinking water needs, which would significantly alter the downstream salinity of Apalachicola Bay. And the Supreme Court actually ruled in Georgia's favor in the case, which makes it likely that there'll be an increasing amount of freshwater diversion upstream, reducing the amount of freshwater inflow to Apalachicola Bay. The other issue is sea level rise. Global sea level rise will affect many parts of Florida. The right there shows what areas will be underwater with 2 meters of sea level rise in the area around Apalachicola. In Apalachicola Bay, sea level rise will result in changes to salinity levels and habitat distribution. When combined with reduced freshwater input, Apalachicola Bay would experience a significant salinity increase. Now, there's a need for more research on the ecological consequences of such salinity changes, particularly in regards to the effects on species populations and trophic dynamics. So that's what I'm interested in. The question I'm aiming to address is, how will freshwater reduction and sea level rise affect the Apalachicola Bay food web? I'll be using a coupled hydrodynamic and food web modeling approach to simulate salinity changes and species responses. I'm collaborating with researchers at Tulane University to construct a Delft 3D hydrodynamic model to represent changes in river flow, salinity, and habitat conditions in Apalachicola Bay. Construction of this model has been completed, and I'm creating the food web model myself using EcoPath with EcoSim and EcoSpace, which is a food web modeling software, also known as EWE, and that will incorporate species biomasses, trophic interactions, and species distributions. The models rely on ANERR's 2 decades worth of biological and environmental monitoring data. Currently, the EcoPath base of the food web model has been completed. Calibration and EcoSim is being finalized, and the EcoSpace component is under development. The completed food web model and salinity change simulations are being used to interpret changes in species abundances and distributions in Apalachicola Bay in response to changing salinity regimes. I've also developed an online survey for Apalachicola Bay stakeholders. They'll be used to assess stakeholder knowledge and perceptions on species in Apalachicola Bay, as well as environmental changes. Development of this survey has been completed, and it's currently collecting responses. All right, so getting into how the models work, we'll start with the EWE food web model. The EcoPath component is used to create a mass balance snapshot of the food web, which means that the energy input balances the energy output for the system. For the Apalachicola Bay model, the initial conditions in EcoPath represent an average of the years 2000 to 2003, because these are the first few years for which monitoring data is available. The full set of species monitoring data used to develop the food web model comes from ANERR's trawl survey data from 2000 to 2019. These data were collected at the numbered sampling sites on the map there. The list of species in the food web model is only a partial representation of the system, but I based the list on the top 99% of species caught across all years of the trawl surveys. And to account for other species who are also important members of the food web, but not necessarily well represented in ANERR's surveys, I also supplemented the list using data from FWC's Fisheries Independent Monitoring Surveys and previous Northern Gulf of Mexico food web modeling studies. Once the food web model species list is developed, EcoPath uses 4 parameters to ensure the model is mass balanced. These are biomass, production to biomass ratio, or P to B, consumption to biomass ratio, or Q to B, and ecotrophic efficiency, or EE. This table is part of the species list for the Apalachicola Bay food web model, and you can see the different parameter values for each of the species groups. Species biomass was calculated by converting the length measurements collected during ANERR's trawl surveys into weights using length-weight regression equations. Several of the length-weight regression equations I developed myself by measuring specimens collected from the trawl surveys, and for the others I used information from previous studies. The P to B and Q to B parameters indicate how quickly the biomass is potentially changing and the number of times a population consumes itself in a year. The values for both of these were derived from previous Gulf of Mexico food web modeling studies. With the input of the other 3 parameters, EE was calculated by ecopath, and that will serve as an indicator of whether a species is being overconsumed in the system. The next step in building the food web model was creating a diet matrix that represents the different proportions of prey items in each predator's diet. So this is an image of the diet matrix I developed. Across the top are the predators, and the numbers indicate the proportion of a certain prey item in each predator's diet. So each of these columns is going to sum to 1. I based the diet proportions for each predator group on information reported by previous studies and available through online databases. There we go. Okay. Oh, whoops. Ooh, how do I go back? Okay, there we go.
You can use your arrow keys on the keyboard to
the next
navigate
step.
back and forth.
Okay, yeah, I figured it out, thanks. The next step in building the food web model was creating fishing fleet landing amounts. And for this model, I included both commercial and recreational fishing fleets. The commercial fleet landings were based on FWC trip ticket data, and recreational landings were based on NOAA Marine Recreational Information Program surveys. Once all the fishing information was entered, along with the rest of the ecopath components, I checked to see whether the model was mass balanced. And this is done by looking back at those EE values I mentioned earlier. If the values indicate a species is being overconsumed in the system, then adjustments are made to fishing effort or the diet matrix until a reasonable level of consumption is reflected. After making all those adjustments, the ecopath food web model of Apalachicola Bay is now complete. All right, and this is a flow diagram output by ecopath that gives a visualization of the Apalachicola Bay food web as represented in the model. And we can see all the different connections between the various trophic groups as well as fishing fleets. And all of these trophic connections are taken into account as we move forward in the food web model analysis. So with the ecopath component of the model complete, the next step is calibration and ecosim. That's the time dynamic component of EWE. EcoSim uses the full 20-year time series of available data to calibrate the model over a continuous time period, and the successfully calibrated model is used for further simulations to represent changes in species biomass over time. So here's an overview of the different parameters that were input into EcoSim. Using bay anchovy as an example, we have time series of species biomass from 2000 to 2019. Biomass time series were also created for all other trawl caught species in the model. Next, we have environmental time series across the 20 years. This one shows salinity, and these data came from the system-wide monitoring program stations throughout Apalachicola Bay. And salinity is just one environmental variable that affects species abundance, but we know it's a pretty major factor in Apalachicola Bay. Species responses to environmental variables are dictated through species response curves. And this is the salinity response curve for bay anchovy. The plateau of the curve indicates the optimum salinity range for bay anchovy, and the rest of the curve encompasses the overall salinity tolerance. Lastly, we have time series of fishing effort. The graph on the far right there is for the bait fish fishery, which bay anchovy are a part of, and time series were also created for all other fishing fleets in the model. Once EcoSim has all those parameters input, it calibrates the model by outputting its own estimate of species biomass over time. The graph on the right is the time series of bay anchovy biomass output by EcoSim, with the observed data represented as points. We can particularly see how EcoSim took the salinity tolerance of bay anchovy into account in this output. The optimum salinity level for bay anchovy shown in the response curve is between about 5 and 15. And we see that EcoSim shows bay anchovy biomass decreasing over 2000 to 2010 during the period where salinity was increasing And then once salinity levels start to drop back down closer to the optimum tolerance range, biomass starts increasing again. The changes in biomass of popular prey species like bay anchovy influence the biomass trends for upper trophic level species as well. So here we see Ecosim's output of sand sea trout biomass compared with that of bay anchovy. Bay anchovy is a common prey item for sand sea trout. Similar trends over most of the 20 years. Ecosim gives unique output of biomass for each species in the model. The biomass output by Ecosim is compared with the observed data to determine a sum of squares, and the model version with the lowest sum of squares is used for further analysis. Right, the remaining components of this modeling analysis are the Delft 3D hydrodynamic model and ecospace. The hydrodynamic model has been developed by collaborators at Tulane University. It incorporates data on water quality and hydrological conditions. Scenarios that simulate a changing salinity regime will be run through the model. And these scenarios will involve a variety of river flow conditions based on historical measures of river flow and regulations discussed by the U.S. Army Corps of Engineers. The sea level rise conditions will be either high or low and are based on sea level rise predictions made by the IPCC. The different river flow and sea level rise parameters will be run in combination with each other. And these scenarios are applied to the hydrodynamic model, and that model output will serve as the input for the ecospace spatial temporal framework of EWE. This ecospace component is currently still under development, but once completed, it will be used to represent Apalachicola Bay in the form of a gridded base map, and the cells of this map will be able to receive environmental input from the hydrodynamic model and species biomass input from the ecopath and ecosim components. Right, so the image on the left here is from the Apalachicola Bay hydrodynamic model, and it shows bathymetry and a time series of water level. Simulations from the hydrodynamic model will cause the environmental conditions in ecospace to change, and ecospace will then take into account the environmental tolerances of species in the food web model and will give an output similar to the one shown on the right here. And that reflects changes in species distributions in response to different scenarios. And this is actually an example from a study done in Louisiana. But once completed, the Apalachicola Bay model will be able to produce an output similar to this. So the last component of this study is the stakeholder survey. For the context of this project, a stakeholder is being defined as anyone who lives or works in the Apalachicola Bay system. I developed an online survey with questions aimed to assess local knowledge and perceptions of species and environmental changes in Apalachicola Bay. The results will be used to determine particular species of interest for the project analyses and compare local knowledge with observed data trends. Currently, the survey is up and running, and many of you in the symposium likely qualify as Apalachicola Bay stakeholders yourselves. So if you haven't taken the survey yet, please do. I've included the QR code there and a link, so if you want to scan the code or take a picture, pull the survey up on your device for later, you can. I'll also have the QR code and link again at the end in case you miss it. Okay, there we go. So that's the big update on, going too fast. That's the update on my research project, modeling the Apalachicola Bay food web response to changing salinity regimes. My time as a Davidson Fellow will be up at the end of July, so the final project results will be complete by then, and I plan on having a few publications come out of this. I'm hoping the results will be useful for assessing implications of salinity changes for species relevant to fishing or conservation interests. And once completed, the model will be available to be used as a tool by ANERR or other interested parties that can provide insight into coastal management practices for the area. I've really enjoyed my time working on this project as a Davidson Fellow so far, and I'm looking forward to seeing it through to the end. We'll see if it, okay, there we go. All right, thanks for listening. I want to thank everyone at ANERR who's helped me out. You all have been wonderful to work with. Thank you to the folks at Tulane who are collaborating with me on the hydrodynamic model, and thank you to my lab for always helping me out as well. So for those of you who are interested in taking the stakeholder survey, I have the information there again. Otherwise, I'm happy to take questions.
Thank you so much, Kira. Do we have any questions? Oh, I see one in the question box. Hold on. Are you able to assess the impact of the cut on salinity as freshwater input decreases? So the influence of Sykes cut.
I didn't catch that. Oh, sorry, it was like cutting in and out, so I didn't catch.
Let me try, our bandwidth is getting a little dicey. Are you able to assess the impact of Sykes cut on salinity as freshwater input decreases?
Okay, so the question was assessing the input of Sykes cut on salinity as freshwater input decreases. Is that right?
Yes, as part of the model.
Okay. Okay, yeah, so yeah, that would definitely be one of the abilities of the model. Yeah, right now I haven't gotten as much into the ecospace component yet, so right now the model is just kind of a general representation of like Apalachicola Bay as a whole. But once we get into developing ecospace more, we'll be able to pick out more of the geographic sites and kind of we can narrow in the focus on certain areas. So yeah, that we'd be able to do that.
Great, thank you. I don't see any other questions or hands raised. See if Kennedy or Anita can see anything. So if you'd like to connect with Kira, please visit the Padlet and enter in your contact information or questions or comments. Greatly appreciated. Also, if you're willing to take part in her stakeholder survey, either scan the QR code now or reach out to her and I'm sure she'll send it to you. So thank you so much, Kira. Great job.
Thank you.
And you're welcome. So at this point, we're going to take a quick break and we're going to reconvene at 10:45. And so everyone stretch your legs, grab some coffee, and we'll see you back at 10:45. Thank you.
Hi, everyone. So we're going to go ahead and jump back into the second half of our morning presentations. Welcome back. My name is Kim Wren. I'm the assistant manager here at the Apalachicola Reserve. I'm going to lead this next session that'll take us to lunch and our wrap up. It's my pleasure to introduce our mid-morning speakers, starting with Dr. Renee Collini. She works with the Program for Local Adaptation to Climate Effects, Sea Level Rise or PLACE, and she will be talking about what's new with sea level rise in Apalachicola. So great to see you, Renee. I'll turn it over to you.
Thanks, Kim, and thanks everybody for coming today. I'm going to try and get a lot of information into a short amount of time, so just please reach out if afterwards you have any questions, but I am going to try to leave a lot of time for questions at the end. So just to give you a sense of what I'm going to be talking about today, I'm going to give you all an update on some newly released sea level rise science. We're going to go over some of how to use that in terms of decision making and uncertainty, and then I'll cap it off with just a few resources that you can use, and hopefully we'll have time for discussion if I can time things out well. So first, I'm just going to jump right into it. We have new sea level rise scenarios that were updated this year for 2022. These are the global scenarios, and I just kind of want to orient you to the idea. You're going to see a lot of these graphs. There's time across the bottom, and then going up and down the y-axis, we have feet of sea level rise, and it goes out to 2100, and there's 5 scenarios: low, intermediate, high, and high. Now, sometimes people take a look at this and they think it means that the researchers who put these numbers out are just guessing or that they don't know what they're doing, because that's still a fairly large range. But the reality is that there are three sort of major reasons for why we can't just have a single number for how much seas are going to rise. And understanding this helps us understand how to make decisions with the information. So the first is we don't know how much carbon is going to be in the atmosphere. So you can see here CO2 emissions over time. It's time across the bottom again. On one axis, we have CO2 in the atmosphere. On the other, we have temperature. That as that CO2 goes up, so do temperatures. The problem is scientists, at least environmental scientists, can't predict what's going to happen, what the actions are going to be in terms of climate change and how much carbon emissions are going to be out in the world. And so we have to sort of account for a variety of futures. Additionally, as you saw in that same graph, if you look at it again, that temperature as it tracks up, it doesn't just have a straight line, it wiggles. There's natural variability. And it's not just temperature that has a wiggle, everything in nature wiggles. And so if you think about the timing where some of those wiggles could line up and amplify each other, and sometimes they could cancel each other out, and all the many processes in nature that are wiggling, there's just sort of some natural processes or some ranges we've got to account for. And then the last thing is that the ice sheet science, right? We're still getting better at this. We're still trying to understand exactly what could happen and how quickly that would happen. But the 2022 scenarios actually just took a big jump forward in this information. So what's in that report? There's a lot in the report. I'm not going to get into all the details, but the two things for this talk I wanted you to know about is one, there are updated global, regional, and local sea level rise projections, and they span from 2000 to 2150, but you can get these in increments for any decade. And something new are extrapolating observations. So the tide station Apalachicola has this. They took data from 1970 to 2020, so a 50-year time, and they looked at how much seas were rising, but also the acceleration, the rate of how much faster they were starting to rise, and then projected that out another 30 years, just extrapolated that on forward. So if you think about that and the things we know and the things we know we don't know, such as how much carbon is going to be emitted, we can reframe this range. Instead of thinking about it as a big guess, we realize that this is the range of what's scientifically possible, that we know which scenarios we could, how much sea level rise we could see given different potential futures. But it doesn't mean they're all equally as likely. And so I'm going to walk you through this figure. Don't get overwhelmed. The far column on the left, if you look at it, that is the scenario, right? We already covered those low, intermediate, low, intermediate, high, and high. And then you see under different emissions futures, the probability of that scenario being exceeded. So let's just stay with these middle three here, low, high, and very high emissions. If you look at low emissions, that low sea level rise scenario is still really likely to be exceeded. But as you move down, you see those higher scenarios are much less likely to be seen. Less emissions, less chance of having those higher numbers of sea level rise. If you look at the very high emission scenario, you see it does still get lower. There's still less chance of seeing that high and intermediate high, but there's a lot greater chance of seeing like that intermediate low or the intermediate than compared to lower emissions. But again, this information, the lower scenarios are much more likely to be exceeded than those higher ones, is something we can use for planning. I'm quickly going to talk about this column on the right, where you have very high emissions and what are called low confidence processes. So when I said the ice sheet science was this thing to still watch, there's still some discussion, a lack of certainty around this, some processes that could cause really rapid disintegration of those ice sheets. When I say rapid, I don't mean months, I mean over a few decades, but it still could have a big impact if that actually happened. But there's not consensus, right? It's low confidence on if it would happen and if it did, what that would look like. And so keeping in mind that it could happen and assuming that it does happen, we can also look at how much the likelihood is of those scenarios being exceeded. We didn't have this kind of breakdown previously. This is something else that's new with the report. But the bottom line is still there that the lower scenarios are still much more likely to be exceeded versus some of those higher scenarios. It's just if those low confidence processes happen, we'll see a greater chance of exceeding those scenarios. So before we get into what to do with that and how you make decisions with that, I wanted to just introduce y'all to the Apalachicola scenarios. I don't know how many of you gotten to see the science yet for Appalachia specifically. When I wrote this abstract, I didn't think that the science was going to be released on Tuesday. I thought it was going to be a few months out. But anyway, so what you're seeing here are the projections specifically for Apalachicola. Again, it's that low through high. but it also has those extrapolated observations. And so you see here the black line, those are the extrapolated obs, and they only go out to 2050, because after 2050, what we've seen happening with sea level rise, the processes influencing it will look pretty different moving forward. So just a couple notes on that and how to use this information. The observations you probably have noticed are higher than all of the sea level rise projections for Apalachicola right now. That's because we have seen recently a pretty intense acceleration of sea level rise. And that's an observed trend, not just for Apalachicola, but the entire northeastern Gulf, basically Mississippi through Cedar Key. And it's not just at our tide stations, but it's also on the ocean. So it's not necessarily about land movement. There's something going on in the ocean that is making our seas accelerate in how fast they're rising locally. The question that we still don't know the answer to is if that will be sustained beyond the next 5 or 10 years, and that acceleration will continue to happen because of climate change, or if there may be some cyclical process that hasn't been accounted for yet that is going to see that acceleration in the short term, but maybe it could slow down a bit in the future. So the bottom line is, if you're looking out 5 or 10 years, lean into those extrapolated observations, because that's a true signal. We are seeing an acceleration in sea level rise locally. But if you're looking out beyond that, there are other skills, other approaches for thinking about sea level rise that would make more sense to use, and I'm going to cover those next. So seas are rising, we know they're going up, we're not entirely sure by how much, so how do you use that information in planning? The first thing is we have been making decisions about an uncertain future for a long time. There are already approaches that exist for the fact that we can't predict the future, right? I'm going to go over 3 of them. One is risk tolerance, the other is scenario planning, and then the last one are adaptation pathways. Each of these have a rich background and way to apply them. I'm going to give them a skim, so please feel free to reach out if you have questions about these. So risk tolerance is really thinking about, okay, if it's going to be a major impact, then I have a low tolerance for risk, but if it floods and it's not going to be the end of the world, it's not going to be a big deal for me, you probably have a pretty high tolerance for risk. That's inherently subjective. But for each project, you can think about certain things to help make the project itself, the risk tolerance a little more objectively decided. And that's including things like the scale, the size of it, the location. And again, this isn't just about proximity to water, but it's also a chance to talk to your stakeholders. So, you know, folks at the bayous of Louisiana are going to feel differently about flood risk than say people who live in a suburb of Mobile. Cost or value, this isn't about monetary only, it's also about cultural importance or value. Function, is it serving a lot of people in a really critical way? You know, you need it to work. That means you're probably going to have a low tolerance for risk. Length of time, things that you want to last a long time probably shouldn't flood often. And then the bullet's gone, that's my fault. One other thing is adaptive capacity. If you can easily move something or adapt it after it's been implemented, then your tolerance may be a little bit higher. But if it's stuck there for good and you can't do anything after it's done, it doesn't have a lot of capacity to adapt, your tolerance for risk will be a little lower. So just to give you an example, how you pull all this together, if you have a low tolerance for risk, you're going to be looking at these scenarios that have a low chance of happening, but if they did happen, would have a big impact. If you have a moderate tolerance for risk, then you're probably going to go here in the middle ground with the intermediate scenario, because it has a moderate chance of happening. And if it did and it got exceeded, it would have a moderate impact. As scale, I used intermediate for my house. It was important to me, but not an entire county, right? And then if you have a high tolerance for risk, you're really only going to plan for these scenarios you're really sure are going to be exceeded. You're just going to put in sort of that bare minimum of avoidance. So as an example, if you had a hospital in a coastal county, you're going to think about risk tolerance. For me, that's a low tolerance. It's critical. It serves a lot of people. You want it to last a long time. So that means from scenarios, I'm going to look at the intermediate high or high. So if you go and get your scenarios for your local area, again, I highly recommend using local data when you can, when it makes sense. So if I'm in this coastal county sea level rise scenarios today, and I'm looking ahead 50 years to 2070, and I'm looking at those high and intermediate high scenarios, now in my low risk tolerance situation, instead of planning for somewhere between, 2 and 7 feet of sea level rise, I'm going to look at about 3 feet of sea level rise when I'm thinking about how I'm going to design and implement this hospital. So I'm going to switch gears and talk about scenario planning. Scenario planning is where you're taking a look at a bunch of different futures and management actions and how well they do under a variety of futures to decide which one may be the most robust under a bunch of futures. So just thinking about what that means here, this is a very basic example. say you have sea level rise and land use change you're looking at. That right there is 4 different scenarios with a bunch of sea level rise and not much land use change to not a lot of sea level rise and not a lot of land change and the other 2 iterations of that. And then if you're trying to like preserve your marsh health and extent, there's a lot of management options you could take. So then if you look at, say, you know, again, this is just a simplified version, you know, basic stoplight colors, red mean not a lot of benefit, yellow means moderate, green means lots of benefit. You start to see how under a variety of things that could happen, these management actions respond. And it doesn't mean you have to just look at one. Say you're looking at a portfolio of actions, like on this slide where you've got multiple actions coming together. Well, this row here that's got some green and some yellow, no matter what happens, it does okay. That may be your best choice in scenario planning. The last one are adaptation pathways. In adaptation pathways, this is about avoiding making decisions in really dynamic systems until you absolutely need to. So it's about stringing together strategies for like the lowest cost or the least intensive that'll be effective now, and then understanding when you hit a tipping point so that that scenario will no longer be effective. Say you're trying to prevent a barrier island from breaching, and this really simple solution will work, this adaptation strategy will work, but then after about a half a foot of sea level rise, it won't be as ineffective, so you need to move on to something that costs a little bit more money. So like I said, it's not new to make these decisions in an uncertain future. We have lots of options. I just want to quickly talk about when you might want to use each one. Risk tolerance is great for stable projects, non-living structures. I mean, you're not going to build a marsh platform for 3 feet extra of sea level rise because then your marsh won't be a marsh, right? But for hardened infrastructure and really critical projects or projects that are really not critical, again, like a shed or something, risk tolerance makes sense. It's not necessarily great in dynamic environments where you see a lot of change over time. So you could invest for say 5 feet of sea level rise, but then you're 1 hurricane away from the whole system looking different and that being a waste of your money. For scenario planning, it is computationally expensive, but that means it's really great for things like complex situations with lots of stuff interacting. It's really useful for marsh and other types of natural resource management. And these things that are sort of in the middle, right? You don't want to use scenario planning when it's a critical function and it must function in the worst case scenario, because that's just a waste of your time. You know exactly what thing you need to look for. Same thing with really low important stuff. It's a lot of effort in scenario planning for not a lot of return. And then finally, adaptation pathways, like I said before, great for dynamic systems and also in situations where you don't have a lot of capital on hand in communities that are trying to build up to this. You can invest slowly in strategies that build over time, and you accelerate that as you see the resulting sea level rise. So I'm flying through this. I think I have like a minute left. I just wanted to touch on some resources. Some of these are new and some of these are upcoming. There's a new sea level rise tool from NASA that, for those of you who've seen my 2-pagers, it kind of replaces that, where you can go in and you can click on a specific station. So like we could zoom in here to Apalachicola, and if you click on it, it'll give you those same data I was showing you earlier. It'll show you your projections, you can get your extrapolated observations, and you can see here where you're able to get your data. So if you don't like the look and feel of this one, you can just download those same data and make your own graphs. Something else to consider, knowing how much sea level rise to plan for is just a really small step. You also need to make progress in terms of translating that into some kind of impact, right? So for example, high tide. The NOAA sea level rise viewer has been updated to have these new scenarios too. So if, say we were looking at Apalachicola and we wanted to go look at 4 feet of sea level rise and see what high tide looked like, you're able to do that there. And you can download those GIS files if you'd like to put them onto your own maps. In our part of the country, specifically in this region, because of research done at ANERR, we actually have future sea level rise and storm surge. So how storm surge will change with sea level rise. Again, you just, here's storm surge, a 1% annual chance today. Here's what it would look like with about 4 feet of sea level rise. So these are data where you can go and start to think a little more, broadly about the impacts. I'm just flagging really quickly that we also have data coming. Hopefully in the next few months, they'll be accessible, where we're looking at when those changes in storm surge happen, what additional things are at risk from a socioeconomic perspective, buildings, people, bridges, critical facilities. So those data, we're actually like road testing the tool now. So if you're interested in participating in that, let me know. But those data are coming down the pipeline. And then this is the tip of the iceberg, right? There's lots of tools out there. So there is a tool for tools, if you will. It's called Gulftree. It helps you navigate all the other tools that are out there. You just answer about 5 questions and it'll narrow down the over 100 climate resilience tools we have in the Gulf to a few that could best meet your needs. So here's the recap. I'm not going to read it because I'd rather get to questions, but just know that we have some planning power. We have some information. The sea level rise science is moving forward, but we have enough that we don't need to wait. We can move forward and start being prepared now. How'd I do, Kim? Are there any questions?
You did great. Great information, great resources. Do we have any questions, Anita, for Renee?
Working on it.
Let's see if we got anybody's hands raised.
Not seeing any hands raised. Whoop, there goes a hand. Cindy Clark.
Hey, Cindy.
You can unmute yourself or just unmute yourself and ask Cindy.
Am I unmuted now?
Yeah, we can
You're
hear you.
unmuted.
Super. Thank you. This is great news for us, especially because it's on our mind right now. And I know I have been pestering people about new models, so this is awesome news. I'm particularly interested in the storm surge aspect of this because we have modeled or used your models for the sea level rise. But so are you saying that the new models will incorporate storm surge?
So the models that were put out that gave us the sea level rise curves in that task force report that came out this week, that's simply the water elevation change. The storm surge models, and I think actually Christine Buckle already sent those to you, that actually is the 1% annual chance flood event with sea level rise. So what that 1% annual chance event would look like with 1.5 feet of sea level rise or with 4 feet of sea level rise. So that is available. That was completed a few years ago, but it's still relevant because what you'll do is you'll be like, okay, well, we have this, you know, we're likely to hit 1.5 feet in this time frame within the next 30 years. This is what surge could look like in the next 30 years.
Perfect. Thank you. This is great news. That was it.
Great, thank you, Cindy. And there was a comment from Nigel Temple, great resource and explanation of risk tolerance. Thank you, Renee.
My pleasure. And just to clarify, there's a lot more behind all 3 of those approaches. And these are sort of conceptual. In practice, they'll look, you know, they'll reflect the reality of the projects that you're working on. But I'm always happy to talk about it if anyone has any questions.
Thank you, Renee. And remember, you can visit our Padlet if you want to contact Renee. We'll put that link up again before we leave. So next, I'd like to introduce Sara Martin. She's also with the Program for Local Adaptation to Climate Effects, Sea Level Rise or Place. And she will be talking about collecting stakeholder perspectives on marsh modeling to inform modeling and improve decision making. So I'll turn it over to you, Sara.
Okay, sorry, I was waiting to be able to unmute. So, hi, I'm Sara. I'm with Place, like was said. Okay. Do I have control of the screen yet? Oh, it says I do.
You do. You literally click once into the GoToWebinar interface and you're ready to go.
All right. So I'm going to be talking about this effort that we've been doing to collect stakeholder perspectives on marsh modeling to improve decision making. And this is really part of a larger project that I'm going to describe a little bit. But it all started with this 2018 workshop where marsh modelers and stakeholders were brought together in one workshop to compare and discuss the outputs of 4 marsh habitat change models. And basically they were given these maps that look kind of like this one, where it compared 2 habitat change models to see where they agreed and didn't agree. And so they talked about like how you could apply this kind of information, what else they might need, that sort of thing. And one of the big takeaways from this workshop was the need for a retrospective analysis in which you input historical data into the modeling and see how well it projects things that we already know happened. And the modelers and stakeholders felt like this kind of analysis would be really useful for enhancing guidance for decision making, but also for informing future modeling. So that brings us to our current project. So this is the bigger project that I was speaking of. It's called Facilitating Accurate and Effective Application of Marsh Modeling Outputs. And for this project, we're going to be bringing we're going to be bringing the Marsh modelers into a workshop with the project team to determine how to do the Marsh model retrospective analyses. So kind of the nuts and bolts, what kind of inputs to put in it, where can we do it, that kind of stuff. But this time, stakeholders are not included in the workshop because it is very technical. But stakeholder perspectives are important. Any sort of outputs or from this analysis, the idea is for stakeholders and decision makers to be able to use them in their decision making capacities. So to include the stakeholders in the process, we did interviews with people who use Marsh model outputs and other decision makers who use the kind of information from it. Even if they've never actually looked at the model themselves, they use information that comes from modeling. So there were kind of three main ideas that we were thinking about when going into these interviews. How do stakeholders use the Marsh models or Marsh model outputs? If they're not using Marsh models, why not? And then what is it that they really want out of them? What kind of outputs do they want to see? What kind of inputs are they hoping that the models take into consideration, time steps, all those kinds of things. So the interviews were loosely structured conversations. We did them all on Zoom, WebEx, those kind of platforms. That way they could be recorded and we would have transcripts that we could download. And this was really essential so that we could review the conversations and be able to do our analyses and pull out the information from the interviews rather than just depending on notes that we took at the time. And so the conversations followed these kind of 9 questions, and I'm not going to read them all or anything. I know there's a lot of words on the screen, but what I wanted to point out is that most of our questions had to do with how they use Marsh models, what kind of inputs do they like, what do they want to get out of it, questions like that really had to do with the models and how you use them. The next set of questions had to do with what they would want to see out of the retrospective, like what kind of outputs, how should we communicate it, those kinds of things. So interviewed 11 environmental professionals. As far as affiliations, you'll see that a large portion of them were associated with the National Estuarine Research Reserves. And this was important to us because the people who work at the reserves, they are stakeholders and users of Marsh models, but also they're often the people who are giving the information from models to other stakeholders. So they kind of do both parts. It's really important that they understand the models and also we understand how they're using them. And then as far as the area that we were covering, it was mostly North Carolina and the northern Gulf of Mexico. And this was where our team is working and also is where a lot of the models that we're considering for the retrospective analysis have already been ran. Okay, so I'm going to go over some of the results. I'm not going all of them, just kind of the ones that I think would be more interesting for today's discussion. So the first one, how do stakeholders use Marsh models? You'll see in each of these kind of this pie chart and then the answers that were given. So I'm going to highlight these top ones because this was the majority of our answers. And when you look at them, prioritizing areas for future work, informing research, and assessing vulnerability to sea level rise. These are kind of what we would expect for how people would use marsh models. Lots of marsh models are looking specifically at sea level rise impacts on the habitat. So makes sense you'd use it to plan for that. And then also that they'd use it in planning for future work and research. The other one I wanted to point out was this couple of people who said they don't really use models. And there were a few reasons for that. So, one has to do with this quote here. That's our overall objective for the long term is to acquire lands. Whether or not we're going to see drastic changes to the landscape, we're still going to try to acquire lands. So the long-term changes aren't always necessarily an important driving factor in the actions that are taking place. Other reasons had to do with not necessarily trusting models compared to what they've already seen and what they know, like their own personal knowledge of the area. And then we did have one person who said like their organization just didn't have the capacity to dig into modeling and really like get to understand it. So the next one, what time steps are most useful to stakeholders? This is something I've heard come up in multiple conversations recently, so I thought it would be interesting to showcase here. So the most common answer we got was it depends, or one of the most common. And that makes sense because, you know, different time steps might be ideal for different things. And then the kind of typical 30, 50, 100 years, those are kind of go with what the modeling does already. But we also got a lot of answers for these frequent ones, and which were like really frequent, 5 years or less. And people were understanding that that's really like logistically hard to do for models. It can be costly, take a lot of computing power. But the reasons that they wanted to see it, some of the specific management actions they do are done based on changes that happen year to year or over short time spans, like prescribed fire. And then also some of the action plans or planning in general, comprehensive plans, things like that, they might be on 5-year cycles or even shorter cycles. So those shorter time steps can help inform, they felt like could better inform that short planning cycle. All right. So the next one is what kind of outputs other than marsh presence and absence would be most useful to stakeholders? And you can see from this list, the stakeholders we talked to had a lot of ideas. And they were all really interesting and had good reasons and were good things to think about. But I'm going to highlight these top two because the top two being community level changes, which mostly meant like high marsh to low marsh or like one plant species to another plant species, and then ecosystem shifts. So marsh to open water or marsh to upland forest or something. And a lot of models already do this. So it was interesting that it was brought up so many times that maybe it's a matter of stakeholders getting a better understanding of what kind of outputs there already are. Okay, and then how likely are stakeholders to trust the results of our retrospective? So most of the answers were they were willing to consider if, you know, they knew more about the process, if it was difficult or if it's easy and cheap. But I wanted to highlight this unlikely to trust the results. And this has a lot to do with the people or the same reasons that people said they don't really use models in the first place. So I have this one quote here, don't really trust any models, wouldn't say that I know enough to choose any of them over another. So maybe that's something where just some guidance or outreach education can help the stakeholder understand the model outputs better and the modeling process better to where they feel comfortable using it. So some key takeaways from these conversations. While most stakeholders do use models in their decision making, there's a segment that do not. The more outputs and scenarios a model considers increases its usability to stakeholders. So this is kind of obvious, right? Everyone wants a model that's specifically for their location, that's free, that's super easy to use and super easy to understand and can be for any scenario that they need. Stakeholders understand that's not possible, but the more that like a single model can, the more flexibility a single model has, the more likely that it's going to be used. And then also many stakeholders express concerns about transparency in model processes and the uncertainty in the outputs. So the thing with the transparency, maybe that, you know, models have a lot of metadata and a lot of documentation with them, and that could just be a capacity issue for stakeholders. That's a lot to get through. It's a lot to understand and wrap your head around. So that could just be more tools guidance for understanding the actual model itself. And then the uncertainty in the outputs, that had to do more with when there's, you know, this range of things that could happen. It was hard for people to plan within it if they're not sure exactly where it's going to be. And they wanted to know why that uncertainty existed to help them make their decisions. So all in all, I think the key takeaway is that effective training, messaging, guidance, tools, resources, those kinds of things that help simplify the understanding of the model processes themselves, what goes into the model, and also understanding the outputs of what the intended uses are, what the outputs mean, those kinds of things. That's where people can start applying it more often and more effectively in decision making. So what's coming next? I'll be doing more analyses on all these conversations, make sure that we're getting all the good stuff out of the conversations. And then all these results are going to be presented at a workshop, the workshop that we're having with the modelers. That will be in April. And it's going to be used to help inform them just what the stakeholders who use their model outputs, what they're looking for, what they hope to see, where their confusion or gaps in knowledge are. But also to inform the retrospective so that whenever it's being built and ran, their perspective is being taken into account so that it can be used. And then further down the line, our team's going to make sure to develop tools and guidance from the retrospective to help end users really narrow down when they have a specific question they want to, that they'll be able to easily choose which model best suits their location, the time frame they're looking at, and apply it to their decision making. So with that, I'm going to thank Renee, who just spoke, Carrie Schaefer, Sara Spiegler. They all helped with the interviews and with some of the analysis of the interviews. I want to thank everyone who sat and gave the interviews and gave their input because it's very valuable to us. And then also the funder, who is Southeast Climate Adaptation Science Centers. And with that, I'll take any questions. Oh, and feel free, you know, send me an email if you have any questions.
Thank you, Sara. Do we have any questions for Sara or any hands raised?
I don't see any questions in the question box.
Okay.
And I'm looking for hands in case anybody's. I don't see anybody's hand raised.
Okay, well, thank you, Sara, for joining us today. And remember, you can get in contact with Sara by visiting our Padlet.
Yes. Thank you, everyone.
Thank you. All right, next up, I would like to introduce Dr. Havalend Steinmuller with Florida State University, who will be talking today about evaluating coastal wetland vulnerability to sea level rise through surface elevation dynamics within Apalachicola Bay, Florida.
All right, well, thanks, Kim. Last talk of the day, I'll just need to stick with me for 20 more minutes. So I'm going to talk a little bit about surface elevation within Apalachicola Bay, and I just wanted to acknowledge that so much of this has been done by ANERR. These are decadal long data sets that wouldn't be possible without their help. So just to jump right in, as Renee covered so well just a few minutes ago, sea level rise is occurring globally, but this isn't a constant rate in terms of where it occurs. So relative sea level rise on the Gulf Coast, for example, is generally upwards of 5 millimeters per year, with over 1 centimeter per year in some places like coastal Louisiana. And coastal wetlands, since they occupy that interface between the marine and upland systems, are extremely sensitive to sea level rise. So in response to those changes in sea level, coastal wetlands can respond in one of 3 ways. And these responses really depend on a variety of abiotic and biotic factors, but the 2 most important determinants of a wetland's response to sea level are the rate itself and the available sediment supply. So as you can see on this graph on the right, a low rate of relative sea level rise and a high sediment supply is the ideal situation for a wetland. The wetland's living its best life, it's able to persist in the face of change. However, as sediment supply decreases and relative sea level rise increase, the next best option is wetland transgression. So wetlands migrate towards the upland edge of the coastal system to occupy a suitable zone in terms of inundation and salinity. But it's estimated that globally only about 37% of coastal wetlands actually have that space to transgress landward because of human population and development. So the third response to sea level rise is coastal wetland submergence. So in this situation, relative sea level rise rates are so high and sediment supply is so low that the wetlands are unable to keep pace with sea level rise. And the net result is complete conversion to open water and a loss of that wetland habitat entirely. So in these last two situations, the vertical movement of the soil surface becomes a key element in determining wetland vulnerability to sea level rise. Wetland elevation changes are critical predictors in determining how these environments will continue to persist. So elevation in wetlands is a complicated process that incorporates hydrologic, biologic, geologic, and biogeochemical change. So these changes can occur as surface processes or subsurface processes and consist of either changes to exclusively volume or changes to mass and volume of the soil matrix. So in terms of volume changes, there are two processes that impact elevation. The first would be dilation, where the soil matrix swells with the added volume of water. So think of the soil matrix as a sponge. When it's full of water, the sponge increases in volume due to the incompressible nature of water itself. The opposite effect is the equivalent to wringing water out of a sponge. The soil matrix compacts under its own weight without the added volume of the water. So autocompaction lowers the elevation of the wetland surface or subsurface without any associated changes to soil mass. On the other hand, volume and mass changes can occur through multiple other processes, which include sedimentation, where increased inundation can drop sediment on the soil surface. And this effect can be magnified by the presence of vegetation that essentially baffles the sediment, increasing the amount of sediment that's dropped out of the water column. However, when there are especially turbulent flows, scouring can also take place, where there's a net loss of elevation from the soil surface. Another mechanism for elevation increase is organic matter accumulation and root production. Wetlands are hotspots of primary productivity, and that productivity can increase the mass and volume of roots in the soil, as well as contribute to litterfall and detritus that accumulates on the soil surface and increases elevation. The three mechanisms for wetland loss, in this case, are erosion, where sediment is lost from the system via physical processes. There's mortality, where above and below ground biomass dies off, and that associated mass and volume are lost from the soil. And decomposition, where a heterotrophic microbial mineralization of organic components results in a loss of organic constituents in the soil and results in a release of greenhouse gases like CO2 and methane. So as you can tell from that explanation and that figure, elevation in wetlands is a pretty complex process. And that elevation needs to be measured from a reference plane, and that reference plane can also be moving. And we're left with a lot of moving parts that are challenging and time intensive to disentangle. So to get around that issue of trying to make observations of all of those individual moving parts, wetland scientists developed a method to measure cumulative processes to understand net changes to surface elevation. So this technique consists of deploying a set or surface elevation table in the wetland. Sets consist of a rod that's driven down to bedrock or until refusal, which acts as a reference plane for those elevation measurements. There are 9 pins that are attached to the rod that extends parallel to the soil surface and perpendicular to the bedrock rod. And those pins are extended until they touch the soil surface, just barely without force, and the length of the pins above the rod are measured. And this happens at every cardinal direction, so there are 36 individual measurements that are made at one set station to account for any microtopographic deviations. And they're co-located with feldspar marker horizons, and that measures accretion over time. Feldspar is easily identifiable. It's that white layer that you can see in that image. And it's not very heavy, so it's deployed at the wetland surface And we measure the soil profile depth above that feldspar marker divided by our time component to get at the amount of accretion. So when co-located, these two measurements allow for the observation or the calculation of surface elevation change, accretion, erosion, shallow subsidence, and expansion. And all of these are critical to determine the vulnerability of a site to submergence associated with relative sea level rise. As you can see in that map, these set marker horizon stations are located along the Gulf Coast and all around the world to understand coastal vulnerability to sea level rise. And they're deployed in many, many different wetland types that run the gamut of wetlands within the tidal frame. And this brings us to my research question. So I wanted to evaluate the decadal scale elevation trends among 3 different geomorphic settings to understand how each wetland type responds to disturbance. So I had 4 specific questions here. Does surface elevation change and accretion rates differ by geomorphic setting? And is the material that accretes at each site different by that setting? How does setting mediate response to acute disturbance like droughts and hurricanes? And then which geomorphic settings are more vulnerable or resilient to sea level rise? So ANERR has this great long-term data set of surface elevation and accretion data that consists of 2 observations at each site each year since around 2012. So here you can see Stan Lucas and Ethan taking elevation measurements into vastly different looking coastal wetlands, a barrier island site and a river site. And the upper picture in the middle there is that feldspar application. So these marker horizons are reapplied when the previous horizon is no longer visible within the upper 10 centimeters of the soil, so that we have a continuous metric of accretion. And at each site in October of last year, we took cores similar to this one outside of the footprint of the set to minimize disturbance to start to get a picture of what the soils themselves are like and whether accretion is mostly from organic material or inorganic material. And in case you weren't convinced that sea level rise is a major driver of change of these systems, the picture on the lower left is a drowned set. So within 6 years of deployment of this set at Pilot's Cove, it's completely submerged. And instead of marsh vegetation, it's completely colonized by seagrass. So I had 3 different geomorphic settings here. I had 3 river sites, 3 bay sites, and then 3 sites spanning the barrier islands. So let's just jump right into some results for this project. All 3 geomorphic settings displayed shallow subsidence, where accretion rates are greater than the rate of elevation change. So in this picture, you can see box plots of accretion and elevation for each geomorphic setting, the barrier island, the bay, and the river sites. And there's a high degree of variability within the barrier island data that's caused by those 2 drowned sets, which had negative rates of elevation change. So though all sites are experiencing shallow subsidence, the causes of that subsidence differ by setting. So at barrier island sites, the soils are really highly mineral. They have a really high bulk density. They're almost completely sand. And so that shallow subsidence is occurring through autocompaction, where the soils themselves are essentially compressing under their own weight. So it's like building a sandcastle on the beach. As water is squeezed out of that castle, the sand sags because of how heavy it is. But on the other hand, the riverine and bay sites were highly organic. They had very organic soils. So shallow subsidence is likely a result of more organic autocompaction rather than mineral. But if we look at the soils and accretion rates more closely, we can start to see patterns emerge in what components of soil drive accretion. So in this figure, you can see the average accretion rates in millimeters per year on the y-axis and soil organic matter expressed as a percent on the x-axis. So the barrier island sites don't really demonstrate a trend here. They're highly mineral soils with a very, very low organic matter content. The bay sites and the river sites, however, both of which are really organic, show the opposite trend when it comes to accretion rates. So the riverine sites have accretion driven by organic components, which you can see with that positive trajectory. And that means that organic constituents are vital for accretion and maintain that positive elevation trend in these sites. The bay sites show a negative trend, with that negative trend with soil organic matter content, which indicates that despite these soils being really organic, accretion is actually driven by the inorganic components. So sediment subsidies of inorganic material allow these sites to accrete. So what does this mean in terms of sea level rise? It means that the river sites are pretty independent. They're accumulating organic matter just fine, and that organic matter is causing them to continue to accrete. But the bay sites, they're dependent on inorganic sediment subsidies to keep accreting. And this isn't the best situation in terms of all the changes that we've heard about over the last day that have been made to the Apalachicola River. So if sediment supply decreases, then these bay sites are left kind of independent with no sediment available to keep them from submerging. So if we move past accretion, we can look at individual elevation trends. So here on the y-axis, you've got absolute elevation in millimeters and date on the x-axis. So the left graph is the riverine sets, while the right graph is barrier islands. The bay sites aren't actually shown here. Within the river sites, you can see differences in dominant vegetation type. The solid lines are sets that are located in cypress, while the dotted lines are located in everyone's favorite hostile wetland plant, which would be sawgrass. These dotted boxes indicated drought, which was our acute disturbance. Since elevation is so dependent on flooding regime, droughts can impact elevation. So think back to that sponge metaphor from earlier. Without water, there's a decrease in elevation as the soil matrix sponge starts to dry out. And we see that influence more in the sites that are geographically closer to the river. So here you can see that the most severe drought, the first one in terms of time, has a profound effect on elevation in the river sites, decreasing elevation in all but 2 of those cypress sites. The next drought is considerably less severe and has very little of an effect. The bay sites demonstrate a similar trend with slightly less of a variation that's observed with the droughts, even though they're not shown here. And the barrier islands, however, seem pretty resistant to the effects of drought. They're so far removed from the river geographically that it's much less dynamic of an elevation trend. These sites also were impacted by Hurricane Michael in late 2018. And you can see that there's a net positive effect on elevation in the river sites. Hurricanes can deposit rack, which is organic material that ends up becoming detritus on the soil surface, as well as marine sediments that are mobilized and deposited with storm surge. So the sediment subsidy increased elevation pretty drastically, though the effect was more pronounced in the sawgrass sites, which were closer to the river's edge. We don't know how long that sediment subsidy is going to last. There's some research that demonstrates that sediment deposited by storms can result in autocompaction over a longer timescale. But since Hurricane Michael occurred towards the end of this monitoring period, it's going to take more time and more observations to determine how change is going to progress here. The barrier islands appear to be a different beast entirely. They're not drastically affected by storms or hurricanes, but we do see 2 sites drowning over the course of the study. So they're located low in the tidal frame compared to some of the other barrier island sets, but not so low that they'd be at risk for flooding when they were set up. So barrier islands as a geomorphic setting are subject to different mechanisms of change than mainland wetlands. They receive sediment washover and are subject to like barrier island movement and lateral erosion, which might be a potential mechanism for the drowning that we see here. So again, what does this data mean in terms of sea level rise? On the left, there's a graph that shows accretion as those bars, slope of elevation change from the sets as the black points, and organic matter content on a sliding scale of color, with the darker colors indicating more organic soils. So what we see is an elevation deficit across all sites. The black dots, without exception, fall below that yellow dotted line that is sea level rise. So one important thing to note here is how high this rate is. Between 1967 and 2021, sea level rise at Apalachicola Bay is about 2.7 millimeters per year. However, we need to keep in mind that we should compare comparable timescales. So this rate has seen a recent acceleration. And in the timescale of these elevation observations, sea level rise at Apalachicola Bay has increased drastically to about 11 millimeters per year. We also see an accretion deficit in regards to sea level rise at all sites, except 3 riverine sites and 1 barrier island. So those high accretion rates could indicate that those specific sites might be more resilient to sea level rise than others. So if we extrapolate the trends in elevation that we observed at these sites across a larger timescale, You can see this on the right. We can forecast the timeline of when these sites would submerge. So bear in mind that elevation and accretion rates are the only mechanisms at play to determine wetland submergence, but they are some of the most important. So these dates are forecasts that are extrapolated from quite a long time scale. They're not written in stone, but they give a good prediction of when we can expect to see these sites becoming really vulnerable to sea level rise. And I want to just take some time again to acknowledge the ANERR team here. This is a giant amount of data that's measured in a highly manual manner and represents a huge amount of time and effort that they've invested, without which a spatial analysis of these wetlands just wouldn't be possible. So I have a ton of people to thank, and I will take some questions.
Thank you so much, Havalend. Great information. I can see one question on here from Nigel Temple. How does the feldspar fare in an area, in an exposed area, for example, Pilot's Cove?
Yeah, we have had a little bit of trouble with this. So the Pilot's Cove set that drowned, for example, we can no longer have feldspar markers there. The other set is a little bit more protected. It's not like on the beach so much. So when we deposit feldspar, it does actually stick around pretty well at that other site. And it's kind of shaded by the wetland plants. And then there's kind of a bit of a sand berm that kind of protects that site. So the feldspar tends to coagulate a little bit better after we've left it for some time, and we do see accretion over it.
Okay, great. Any other hands up, Anita?
I don't see any other hands. Nigel's question is the only one that I saw. Somebody might pop up here in a second, though. Okay.
All right, well, thank you so much, Havalend, and to the other presenters that joined us on the second day of our symposium. Now I think I'll turn it back over to Jenna or Anita to wrap us up.
Thank you, Kim. And thank you, Havalend. That was so cool. I will take full responsibility for putting sets in the sawgrass. I don't think they've forgiven me yet. I have to go out in April with them. That's my punishment. So I'm sorry, but no, this is so exciting to see. When we installed the sets on the island, those two sites were within Spartina alterniflora, and we thought it would be really interesting to track how that plant community may change. And of course, now it's gone and it's been replaced by seagrass, which is just kind of dumbfounding, but yeah, interesting, very interesting stuff. So thank you for that. And thank you to all of our presenters today, just fantastic. To follow up, we will post this recording on our website, apalachicolareserve.com, as soon as Kennedy's going to probably clean it up and take out some of the pauses and blips that we have. And again, you can access the Padlet. We'll probably keep that open for maybe another week or so. Anita, correct me if I'm wrong. Encourage the speakers to take a look at that and see if anyone has posted a comment or a question or made a connection with them. Again, that's one of the most important outcomes from this sort of event is connecting researchers and furthering the science. And lastly, I'll mention for all of the participants, we will send out an email after, let's see, probably in the next week, I would say. Anita, again, correct me if I'm wrong.
That sounds good.
Next week, evaluation of the symposium. And please let us know how we did and how we can improve for next time. So with that, I will say thank you again to everybody and look forward to hosting again next year. Have a good day.
In person.
In person, we hope.
Yeah.
Fingers crossed. So.